Hello, this is the water-cooled welding bench team from Section 20.
So the objective of this project is to validate the theory that a water-cooled welding bench can effectively regulate the temperature of a metal piece during a welding operation. The ultimate goal is to increase safety in this widely used fabrication technique.
Metal inert gas, MIG welding, is a commonly used fabrication technique. It's used in many industries, including structural, aerospace, automotive, and shipbuilding. It works by using rapid heating of a filler material to create a permanent joint. Cooling time is necessary to allow for safe handling and ideal material properties.
There have been numerous attempts at studying controlling temperatures during a welding session, as there are many benefits to it being successfully implemented. One such prior research noted is effect of heat sinks on cooling time to weld interpass temperature. This paper studies the interpass cooling time, which affects productivity and welding costs. The recommended noted temperature is 500 to 800 Celsius, which leads to the need for multipass welding, with waiting times needed for the weld to cool to be at sufficiently low temperatures. To minimize the number of passes, the interpass temperature should be as low as possible, which also corresponds with longer waiting times. In this work, introducing copper heat sinks adjacent to the weld to reduce the time it takes for the weld to cool down to the interpass temperature is thoroughly analyzed and shown to almost half the waiting time. This can have an overall positive effect on productivity on welding, which is also something that we study in our research.
Experimental setup and test plan. The experimental test compared the temperature change over a 5-minute period after welding with the apparatus and without. The temperatures were taken every 30 seconds using an infrared thermometer. The heat output from the welder is kept constant by keeping the voltage setting, wire feed rate, and weld length constant. The experiment was conducted in a university shop space with multiple welding booths, which were separated with welding curtains. The cooling apparatus was set up in an adjoining booth with the hosing running under the curtain to a welding bench which had the water block set up on it.
The parameters of our experiment were temperature and time, with the dependent variable being the temperature of the metal piece in Celsius, and the independent variable is the time in seconds after the welding has stopped. The controlled variables include water flow rate, fan speed of the radiator, and input power to the pump and radiator.
Here is the test procedure. First, we started by prepping the test plate by sanding the backside to ensure a flat surface. Then 3 parallel lines are marked on the unsanded side and a 5-gallon water bucket is filled. You then plug the power supply and pump, and the fan wiring is connected to the power supply with proper settings. Thermal paste is then applied and spread on the water block surface, and the test plate is clamped on top of it. Then a MIG welder is set to settings 3 and the pump and fan is turned on. The IR thermometer is also set up and aligned with the ends of the marked lines, and the initial temperature is also measured. Finally, a weld is done, and immediately after it, a stopwatch is used to measure the temperature for every 30 seconds for a total of 5 minutes. This is completed for a total of 3 welds. For comparison purposes, these steps are also redone without the cooling apparatus running, with time in between the welds for the plate to naturally cool.
So, during this project, we use a lot of different equipments. Listed here is the drill pump and the drill, which is used to power the drill pump, of course. Then we also have the welder for any welding pieces, as well as the IR thermometer for the temperature. We have the power supply for the entire system, and all of the chemistry test stands to hold the IR thermometer. And also, finally, we have a phone stopwatch to record any times.
Bill of materials. 2 components in our setup were fabricated. one being the cooling apparatus, the other being the water block. Many components were used, and they were obtained through two different means: donation and purchase. Our total for the project cost ended up being $218.97.
The water block was fabricated using A36 steel pulled from the machine shop. All components were hand fitted and then welded at a lower voltage. This resulted in the water block leaking during pressure testing, as there was a lack of proper weld penetration in some areas. This was mitigated by grinding out the leaking areas and then repassing over those areas at a higher voltage. This was done until the material was cherry red, meaning that the cracks were filled.
Risks and hazards associated with this project include flash burns, loss of digits, electric shock from water carrying current, eye damage due to welding arc flash, and burns on the skin from contacting hot metal. For hazard mitigation, Jacob Weller and Mark Hebel from the Camp Machine Shop were consulted regarding this process and ultimately gave final approval. All individuals observing welding were either behind the protective curtain or behind the welder with appropriate PPE. A mesh grill made of hardware cloth was attached to the front of the fan shroud by zip tying it to the cart. A thermal compound was used that was not electrically conductive, and a dedicated ground was welded directly to the test plate so that electricity could flow the path of least resistance and not go through the water. All testers were prohibited from touching the water and metal parts of the cooling system as an extra precaution. We also used the temperature gun to make sure the metal was safe to touch after welding had stopped. A weighted cover was added to the bucket to prevent accidental contact.
For testing, the welder was set to a voltage position of 3 and a wire feed rate of 20 inches per minute. The welds were 3 inches in length and positioned at these three predetermined positions. Each weld was approximately a quarter inch in width, and after every weld pass, the weld temperature was measured using an infrared thermometer. And these resulting temperatures were hand recorded for every 30 seconds for a total of 5 minutes. As can be seen in the data, the addition of the cooling system reduced the time required to cool the plate back to room temperature. Ultimately, the average temperature difference was 11.3 degrees Celsius between the two systems. An additional 350-second system stress test was conducted to test the system's ability to withstand constant welding at the welder's maximum settings. These settings were a voltage position of 6 and a wire feed of 50 inches per minute. As can be seen by these results, the data follows a model of exponential regression, with the weld cooler having a sharper decline in temperature. Exponential decay fitment lines were created using the equation of temperature equal to room temp plus initial temp multiplied by the exponential of negative cool rate times time. The cooling rate was found using a chi-square test connected with Excel's solver function.
So after performing our test, we did an error and uncertainty analysis. For the zero order uncertainty of the measurement device, this will be our IR thermometer. It had a 0.1 degree of uncertainty. And for our instrumental uncertainty, it will also be the IR thermometer with a plus or minus 2 degrees Celsius or 2%, whichever one is greater according to the manufacturer. And for design uncertainty, we had to perform some heat transfer calculation to design the water block. And unfortunately, during the manufacturing process, we were unable to follow the the amount of fins that we wanted to have, which was 20, but we had to reduce it down to 11. The fins also were in the heat transfer calculations were all assumed to be the same height. However, when we were cutting them out, we were unable to keep them to the same height, so they have varying degrees of height. And finally, for the root mean squared with the zero order uncertainty and the um, instrumental uncertainty, it came out to 0.6324. For the calibration, we only had to do the calibration for the IR thermometer, which we done using a cup of ice water to guarantee it has the correct source of 0 degrees Celsius. And for human error, we had the stopwatch time recording, so it varying depending on when they start and stop. Since Thomas will be telling them when to start and stop, and also the temp recording with the IR thermometer, since we couldn't just hold it down and have it constantly read the temperature. So it was 1 or 2 seconds after it finished welding that we was able to get the correct temperature, as well as the welding speed and welding time. As Thomas was doing the weld, he tried to keep it as consistent as possible, but because he's human, there's still some variation with the welding speed and time.
The device built and detailed in this report was able to satisfy the design requirements of cooling and maintaining the metal piece's temperature during a welding process. According to the results, it was able to hold a consistently low temperature within minutes of the weld, which showcased an even better performance than expected. It confirmed the hypothesis that a water-cooled welding bench surface can effectively regulate the temperature of a metal piece during welding operations. There were human errors present, such as the IR thermometer was not constantly updating the temperature in real life, which led to the operator having to cycle the thermometer on and off to update the temperature instead. There were also multiple assumptions made, such as the contacting surface of the metal substrate needing to be adequately flat in relation to the water block surface in order for the application of the thermal place to be smooth. In the future, further analysis of how material properties are affected by the cooling apparatus will also need to be studied. Sizing up the model to a full-size welding bench surface is also another improvement that can be tested in the future. Overall, as the hypothesis for the report was proven to be true, many theoretical improvements can be tested and improved on with the work in this paper as the basis. Here are some of the references that were used for this presentation. Further information and details are present in the report.